So my name is Darren Giacomini. I'm the Director of Network Architecture here at Avaya. And prior to my life here at Avaya, which has been about, give or take 5 months now, I worked for a company called Pelco. Pelco is a video surveillance company out of Fresno, California. And I was their lead network architect with respects to deploying multicast deployments of epic proportions and scale. Now, typically when I tell people that are in the networking world, they immediately say, A, how's your airline miles? And B, you've had a rough life. Traveling from site to site, and your job is literally to troubleshoot and deploy large-scale multicast that's inverted and flipped from what anybody else does. We're not talking about a source here where we're sending out multicast. We're talking about 10,000 sources coming in, and randomly people wanting to view it all over the network. So my job actually over at Pelco prior to coming here, to be honest with you guys, I loved it. My job was to bring in all the different technologies, put them in my lab. They gave me anywhere from 2,000 to 5,000 actual H.264 video feeds, and they said, bring it in and break it. Tell me where it breaks. So my engineers who write the software know where it breaks, and our guys on the support phones upstairs know when we're chasing down a network problem versus a software problem. And I can tell you, we chased a lot more network problems than we did software problems. So I know the guys who Paul and I did a packet pushers presentation not too long ago, and they're probably immediately saying, okay, why are you at Avaya now? And I'll tell you the story of how I got here. It's an interesting story about initially Avaya asked me to come in and test shortest path bridging because we do a lot of this large scale multicast. My response, to be honest with you, was, okay, here's what I'll do. You guys send me all the equipment you want me to test. I'll test PIM over OSPF first. Figure out where your weakness is, figure out where I can break it, and then when I'm done, we're going to go back and take a look at multicast. We'll take a look at SPB. So that went back and forth for 5-6 months, and in the meantime, Ed Kohler over here actually slipped me a white paper on SPB. So prior to the gentleman from Avaya coming down into my lab and doing compliance testing and whatnot, of course, I'm like anybody else in this room, I'm going to grab that white paper and I'm going to read it front to back so I know the technology before they show up. The lights started to go on. The things that go wrong with multicast, with what I dealt with on a regular basis, are solved by what they're doing. By the time they got in, I have a small pre-staging lab, 40 to 100 cameras. I said, you know what, let's just set it up real quick. Set it up. So we went in, they walked me through, and I must have said 5 to 10 times to the guy walking me through it, granted I knew nothing about SPB or configuration of it. I said, wait a minute, this cannot be all I have to do to get multicast running in this environment. You cannot be all the command line I have to do. So I went through, to this day, even with my replacement who took my place at that company, with respects to Avaya, Pelco has never tested OSPF and PIM in any configuration. And the reason being is, it was pointless. The reconvergence that I saw on this when the network was broken, I'll be honest with you. Ed and I were going to this thing, and he was on the phone with me actually, and I'm actually trying to break this. I'm taking the links, primary links coming in for over 1,000 multicast feeds, and I'm just doing this. Okay, that is network death for PIM.
And I'm on the other end of the phone. And
I am sitting there, and then immediately I shifted to, okay, I grabbed my guy and said, okay, record this. Record this. Pull the video up and record this. I want to go show executive staff what this can do. And I'm just sitting there toggling the links and toggling links. And I went for about 30 minutes. And I said, this is unbelievable. I mean, this is phenomenal. And lo and behold, I had to make a decision whether I want to sit on the sidelines and read about another protocol that I think is going to change the game or jump in and get involved with it. And I made the choice to jump in and get involved with it. So given that, we're going to talk about, and I don't want anybody here to leave with the concept of this is a protocol designed to run surveillance. It's great for it, right? It can do IPTV. It can do paging systems like Vocera that run in hospitals. It can do any type of multicast application. This is going to give you a major enhancement to it of what you can do. From the troubleshooting perspective to the deployment perspective. So I don't want anybody here to leave here thinking this is just for video surveillance, because it's not. Second, we're going to take a look at addressing the inefficiencies. The way that things run today on protocol stacks with respects to PIM, I got to tell you, prior to testing Avaya, every single technology I put through, I could find a way to break the Pelco Endura application. Whether it be black video, whether it be applications lockup, and you see the circle of death come up for Windows, typically you don't come back from that, right? Poor video population time, all of those were things that were in there. And so I started looking at the design perspectives, and when I would typically lay out a multicast network, what it came down to is I would look immediately, okay, where am I going to put my rendezvous points here? Rule of thumb for multicast, where do you put your rendezvous points? As close to the source as possible. If you're at the core of your network, that's easy. What if 10,000 cameras, which is the largest system, 10 to 15,000 was my exiting design with Pelco? And to be honest with you, the only reason I didn't recommend Avaya is because I knew it was going to come here and it was a major conflict of interest. So you look at that and you start talking about putting rendezvous points out where you need to put them, which is out by the sources. Now you're going into auto RP or BSRs and Canada RPs. You're talking Anycast RP with MSTP peering. You're reverse path forward checking. If you ever want to have fun, do MSTP peering, do Anycast RP, forget to turn on the mesh pair feature, and watch your RPF checks just skyrocket. And then realize that every single one of those gets processed by the CPU. Yeah. Then put video surveillance on top of that, and you see some very, very strange outcomes happening in the network.
None of them good.
None of them good. None of them something you would want in critical infrastructure. So when you look at the complexity of the design, what does it really drive here for what you want for a multicast design for video surveillance? Fast, flexible, and most importantly, secure. I got a question for everybody in this room. I know you guys are all technologists. You're just like I am. You love technology, right? But how many of you guys would like to make $33.2 million in 45 minutes? Anybody interested in that? I'll tell you, I am right now. I am interested in making $33.2 million in 45 minutes. Don't build your network right, and I'll give you an avenue. Recently in Australia, I won't say the casino name, but you had a two-man team go in and pull an epic Ocean's 11 event. Two-man team. One guy with a laptop, going through either wireless or wired. They can't define that. The suspect is he went through the wireless to get to the wired. He hacked into the surveillance network, pulled through VLC viewer, pulled up the active cameras that are in the high roller suite poker game. Through pan, tilt, and zoom control, zoomed in on everybody's hand in the room. Through a wireless headset, fed this to a whale, which is a high roller, into the room, when to bet and when not to bet. And on 8 hands in 45 minutes, took $33.2 million out the door, back up to his $30,000 a night villa, until security and police came and kicked the door in and booted him out of the casino at 2 in the morning. And you know what happened to him? You can't come back here anymore. Man, I'll take that deal every day. If Avaya wants to tell me, here's $33.2 million, you cannot come back here anymore, and I'll play golf. I'll find something to do. I can dabble in networking on the side, but I will figure that problem out. So where things broke, we start talking about depletion of resources. And real quickly, I say the rendezvous point is really where I look at. And you look at kind of logistics of what the rendezvous point has to do. Number one, it has to process the PIM register message, which is death for video surveillance, and we'll talk about that in a minute. 2, it has to go in and has to perform RPF checks. How often does it do RPF checks on multicast routes? Every 5 seconds for every route on the network. Scale that. It has to do the prunes and joins. If you happen to be in the shortest path tree, you might be doing forwarding as well. Now, let's hit the memory side. Every S, G entry, 380 bytes plus 150 bytes for every outgoing interface oil list on that. Now take a look at your S, G. 220 bytes plus 150 for outgoing oil list. The bottom line is this is finite, right? You only have so much memory and you only have so much CPU. You keep piling on feeds, eventually you are going to run out. How do we address that? We use technology like Anycast RP. We said, well, I can't do this with one box, so I'm going to use 30. Right? And I'm going to create a mechanism that's going to try to reconverge this quicker. At the end of the day, what you have is, I talked about the register message portion, And this became clear to me when I was actually doing a migration for a casino. Now, bear in mind, a director of a casino is a nervous man during migration. Okay? And the reason being is it only takes about 3 hours before you've exceeded his salary and downtime and they have to shut the doors and he gets escorted out and gets to go look for a new job. So to say that uptime is critical for them might be an understatement. Now you look at this, and while we're migrating this, the integrator that's running it, I won't talk about the vendors, but it was PIM dense mode everywhere. You want to see fun? Walk into a network architecture somebody designed with PIM dense mode with a common VLAN connecting it. I look at all the switches, it's 10.10.1, 10.10.2. You toggle a link and you get IGMP queries all over the place. You get massive flooding going across this. And so we're migrating over to sparse mode. Excellent idea, except they put a sparse mode in the middle, dense mode at the edge for the cameras, dense mode for the viewing, dense mode for the recording. Well, here's the problem. Nobody checked to see if that switch supported sparse dense mode. Now you start flipping the casino over. I got 300 feeds coming up on the wall, sitting there, and they all go black. The director behind me goes, "Hey, excuse me, what's going on here?" Well, it's clear. The video went black. What I need to do is I need you to back off and let me do what you hired me to do, to oversee this, get in there and call up the video streams. So I pull them back up on the wall, and here's what you see. It looks like a strobe light. The video comes up for a second, and I see all the video coming up, and then all of it going black. This is one of those moments where I call where the rubber meets the road on what you read in a book versus reality. And what I saw is exactly this. The mechanism of the register message. Because it's unicast and passing this through, PIM was broken, but the first frame gets in there. Yep. Now, what hit me is, wait a minute, that's a software control process. That is hitting port 0 of the CPU. You were telling me that I just sent 300 1080p frames of video towards the CPU? I look at it, it's spiked through the roof. Then, I go back and I look at the routers at the edge. They're spiking too, the ones that were configured for sparse mode. You know why? Because when this stops sending the soft register message back, they have to switch everything in software for the multicast. Now their CPU is going out. So you have this cascading effect of disaster that's going to happen. Immediately I took all the links from the core and I plugged them back into the old one. I told the integrator, I said, you need to go back to the drawing board. Let's revisit this. We're not going to put this casino at risk. That simply can't happen. There are no rendezvous points inside of SPB. When you're using Fabric Connect, you don't have a rendezvous point. You have actually switches running SPB, and these nodes will run Dijkstra's algorithm to find the shortest path to every other node on the network. So now, when we take that CMAC frame and we embed it inside of a BMAC, basically you're encapsulating this inside of there, and what happens is you generate a dynamic ISID for that multicast group. Those dynamic ISIDs are over 16 million. Once you have that ISID, that node in SPB is going to say, hey, if you want to get to 239.10.0200, attach to ISID 16,100,000. Everybody else becomes aware of that. When this feed starts to flow and becomes active, and this user requests it, all it does is attach to the ISID. That's it. No PIM, no RP, no pegging the CPUs. And what's even more interesting is I'm flowing here natively across the shortest path, and then all of a sudden, somebody in another subnet says, yeah, I want it too. Okay, just join the ISID, it's already there. You're multicast routing without really multicast routing.
Is that an ISID per S, G or star, G?
When you look at it, I'm sorry, what?
Either. So what you can do is actually, so you're saying is, so every time an IGMP join comes from the camera or the receiver, right? It's a routing decision at the edge. And what we can do is, remember I said we can summarize multicast? So you can do a star, G. You could say for 1,000, for IPTV, we can take 1,000 channels. We could say through an access list, for example, 500 channels I want grouped together on this one ISID address. I want another 200 channels on this ISID address, and everything else, these other 300, automatically assign the ISIDs via, as soon as they come in. So instead of just being, in this world, instead of S, G, it's S, G ISID. All right? And we can easily see and control the flows because it's all controlled and routed at the edge.
But we can build a unique tree for every S, G.
It's not
a tree per group.
If you wanted 1,000, don't touch it. It'll automatically start creating an S, G for everyone.
Yep.
Yep.
And at that point, it's literally just bridging from
it is not bridging.
Network, or?
Very clear. This is not a LAN.
Okay.
Right? This is, you turn on IP multicast enable. He's now a router right there. He's a default gateway for this camera, for unicast. So when it came in here for unicast flow, he's going to, in his routing table, he's got a unicast routing table and a multicast. This guy doesn't. He's going to say, okay, I know where that route is. For unicast, it's over there. I'm going to put me as a source to the Ethernet header, him as a destination, and it's going to cut through switch to the core. He's going to see as a destination, rip off the Ethernet header and do a route. But remember, this here is not a bridging core. This is a switch core like MPLS, but without the need of MPLS. Okay? So the multicast, same thing. He sees a source come in and says, okay, I've got a source here. He tells the network, I've got a sender. If you want to join that group, this is the IC you want to do. He over there is a receiver, right? Whenever the IGMP join comes in, he goes, oh, I've got a receiver. I need to join that multicast group, and he'll do it. So now he routes it, puts it on the multicast tree, he gets it, he routes it, and routes it back down to the receiver.
And actually, some of this will be apparent when we do the demo.
Oh, so replication is also pretty important here. It's really important to get away from root bridges. That's all really a rendezvous point is. All right? It's the idea of a suck point for multicast. Okay?
So many different meanings.
That's true. Well, it's really important because it's a source path tree. Whatever multicast we're doing, whether it's the bump traffic of Ethernet or it's actually this kind of multicast feed going to digital signage or IPTV or a camera, the replication points are based on the shortest path. We only replicate where it's the most optimal point to replicate. So you're always on the shortest path. So you're only ever sending one copy of a frame or packet at any given link. It's highly optimized. So when we kill a link or something like that, or kill a box, right, we're just recalculating the tree in a very fast process in Dijkstra. That's why it doesn't affect the service. That's why we don't see packet loss in most networks when it happens.
So implicitly then, multiple sources on the same group have different trees.
Yes, implicitly you're right. We can do that so we control the flow itself. In the table itself, multiple sources off the same node can be grouped into the same tree though. Another level of view onto that, right? So we give you a lot of knobs to play with essentially.
In my environment, I have 1,500 nodes all talking in the same group and listening on that group.
Okay, that's fine.
It had to be sparse mode and tree per source.
Yeah. So that's fully supported. We have a lot of those things as well. Okay, absolutely fully supported. Go ahead, Darren. Sorry.
So where this hits for the video surveillance and where you see the actual kind of performance hit here is when you populate video. When you populate video, and I'm pulling in 10 streams, not a problem. Pretty much anything you put together, it's not going to be an issue. You take a look at like a prison, where they may want to pull up 300 streams by either hitting a script or hitting a button, and they want them all to populate. Talk about sending 300 basically IGMP requests out to a PEM routed model. What are you going to do to that RP? You're going to pound it into dust. And what we see is slow response, block video, and there are environments you can't afford to have that. I sat in a meeting with a hospital one time. You want to talk about a point where you feel stupid. And they refer back and they said, well, we're having problems with our system with respects to code pinks. And I said, okay, it's code pink. I didn't have kids at the time. I did not know what a code pink was. But a code pink is when an infant has become abducted or missing. And that is a huge event at a hospital. They want every camera on, and they want it on now. You can't really deliver that in a scalable model over PEM. And what I saw at that hospital is looking at it, I walked in, and the failure point, the nurse said, come take a look at what I'm going to show you. And there's 32 video streams up. Okay, looks okay. You see that nurse? Yeah. You see her down here? Yeah. Those are two separate rooms. Can't be in two places at once. The video froze on one side. So reconvergence and scalability are huge issues. What we're going to do is we're going to show you guys a demo coming out of my lab downstairs. Right? We're actually going to pull up video streams and we're going to do a reconvergence demo for you guys to show you exactly how fast this can reconverge. Ed's going to drive, right? I'm going to go ahead and walk you through the procedure. And this is the topology we're working off of. The camera, in fact, is actually going to be coming from Brisbane here. And our node that's receiving is going to be down here in Los Angeles. And we're going to watch a reconvergence across these two links. So Ed's going to pull it up. Now granted, okay, we're remoting into this. So remoting into something, you're not going to get the best video, but you're looking at it right now. This particular gentleman doesn't move all that much.
Get him to dance.
Oh, he's going to dance. Somebody signaled him to dance, right? So we're moving around. We've thrown down the gauntlet, and everybody's running out of the field of view of the camera. Okay. So let's just watch this back here. Ed's going to look at and find the unicast address, which is 10.10.0.116. In the world of Pelco, they just put a 239 here. So this becomes 239.10.0.116. So we're going to go ahead and we're going to look that up in the multicast tables. And we're going to take a look at that, and you're going to see some interesting information that we can derive from that.
Hey, how come you don't have to type Command Control Y?
You got a typo there, Ed. It's...
Oh, yeah, I do.
Okay, so when we take a look at this, what we're really looking is for the entry. And we're looking for 239.10.0.116. So we're seeing the source, we're seeing this, and we're seeing it's coming from Brisbane. We can also see the ISID that was generated for it. So what we're going to do is we know it's coming from Brisbane. We're going to layer 2 trace path that back to Brisbane.
Now, one point I want to point out is that this is a very unique multicast table. Anyone who's troubleshot multicast environments knows that what we're about to attempt to do is very difficult. You usually have to go through dozens of tables in order to figure it out. Note how we actually have the actual source IP address, the unicast source IP address of the sending node, the actual multicast group address, the ISID circuit, which is basically the replication tree for us, the actual Dijkstra substrate, which are known as backbone VLAN IDs. That actually handles 2 Dijkstras currently in our deployment. The standard calls for up to 16. Mm-hmm. And through this information, we also have the actual source origin point, that DNS name that Paul referred to, so that we know that that camera is coming from Brisbane just from that table, and we also know the unicast address of the source.
That's the SPB bridge leaf node?
I'm sorry?
That's the SPB leaf
that's
node?
the
That's
router
the terminus.
name.
That's the
CLI
terminus
prompt.
where the source is.
So
exactly.
basically, we're going to take this information, we're going to trace back across 4050, which is the BVID it's using for Brisbane. That's going to trace the path back. So then we know what the video is coming through. We're simply going to shut the interface down on the active one, and we're going to view what happens to the video.
Did you say that ISID is generated for you?
Anything over 16 million for multicast is dynamic ISID generation.
Correct. Now what we're doing is we're running a layer 2 trace route. What this is going to tell us is the actual Ethernet switched path across the topology that that multicast traffic is using.
So Los Angeles currently goes to VSP7K3 in our topology, right? So what we're going to do is we're going to look at the adjacencies, right, and see what port we have VSP7K3 on. We're simply going to take that port, we're going to shut it down because that's the active video flow. We're going to force a reconvergence, and we're going to watch the video.
So the 2 BVIDs, you mentioned the 2 shortest paths. Is this like the equal cost tree thing?
Yes.
2 Dijkstras.
It's equal cost.
2 Dijkstras.
Yep.
Correct.
Exactly what it
and they
is.
are equal cost, exactly.
Now the thing to be aware of though is because we support dual homing into the fabric,
Right.
it's actually 4 trees because we can load balance into it and then we load balance from every node 2 paths out.
Correct.
And that's the thing. This is my memory going back, right? Is that with shortest path bridging, you can have multiple equal cost paths, but typically an ISID is mapped to 1. Because
Yes and no. So when you're talking about a layer 2 or layer 3, really what you're doing in your hashing algorithm is how far you want to look into the packet.
Okay.
Right? So the standard itself, we wrote in the standard that we can do ISIDs go left, ISIDs go right, but you can optimize on top of that. Like for example, when we're doing the IP multicast, or we're doing the IP unicast or IP VPN, we're doing a full 5-tuple hash on the packet and load bounce across
True
the trees.
ECMP.
Yeah, it's true
Right.
ECMP.
Because last time I looked at this was like 2 years ago, right?
Oh, okay, no worries.
So the hop by hop was just still like a dream in someone's head, and
Okay.
Yeah, the left-right thing is really a low ball tiebreaker that was done for L2 VSNs.
That's cool. Thank you. Sorry.
So when looking at this, Ed's going to isolate, you see the VSP7K-3, we're going to shut that port down.
And can you squeeze it?
And we want to squeeze it so we can see the video.
And how many total ISIDs are in the system? Somebody said this number earlier.
16 million.
16,777,215. The number that is actually 4096 exponential. It's a 24-bit field. Ooh. You have to give up 1 for an all zeros. That gives us 16 million.
So I just wrote 16 million. Thank you.
Ed, squeeze it over a little bit more.
Math happens to be a hobby.
Can we bring it over a little bit more so we
You
can
got
see?
it.
Okay, so those guys are not just
Okay,
standing there
so
for
we
no
can
reason.
see that these guys are moving around, they're talking. These guys never talk, so this is really something
They're
to get
never
them
in
to
that
stand
row,
there.
so we know they're being scripted to do this.
So we're just coming in, and we're just going over to interface gig 150. Wait a minute. I got to go to config T first. So we're going into the configuration
Send them a
mode.
beer.
And we'll go in.
Getting some nowhere after this.
So now what I'm going to do is I'm just going to do a shutdown on that port, because we know that is the way the multicast traffic is entering this particular
And actually,
switch
if you
that
look
we're
over
on.
there, it doesn't, I mean, this is really washed it out, but if you actually look up there, you see a much better representation of the video.
Okay, so let's do this.
So we shut it down, quick glitch, and you're done.
Wow.
Now, what this application has the propensity to do in large-scale environments is go black, crash the application, bring the circle of death from Windows that we all love, screen washes out, goes white. All those are bad things. One thing I want to point out before we kind of leave this discussion is this is all inside of a VRF with multiple instances. This is a secure network. Now, this is some advice that I would give to that casino over in Australia. Put your stuff in a secure VRF and I can save you $33.2 million. Okay, because this never could have happened, because when somebody plugged into the network, it simply would have shut them off. Right?
Now to finish, I have to complete my Vanna job. Let me run the trace route again. And basically what you're going to see is that we're now using the alternate path that was available. So the BVID actually shifted.
Stretch it out and run it one more time because you can't see it.
There you go. There you go. So as you can see, we're now going through 4.
Yep.
Now, when I actually enable the port again, we'll run the command again. Steve, we have an edit point.
If that's the worst glitch in your demo, you're doing pretty good.
I actually did that on a YouTube video, an Avaya Mentor video. But as you can see, no impact. If I ran the command again for the L2 trace, we would very easily see that, and I will now expand back out again, and we'll see that we are now back running through VSP3.
So realize, guys, when I ran this, I told you I toggled these links. This is what I saw.
Okay, so I have a question from that, because that was brilliant, and your whole casino thing, I was the data center move team to move U.S. playing cards from Cincinnati to Erlanger, Kentucky, and they have all the federal requirements for cards and dice and cameras. We couldn't lose any of that, and we had all these problems. So yes, get it. Are there ways within the algorithm or the routing protocol or whatever we're calling this, because I'm not sure it's any of these, that if you have in a critical environment and you fail to link, that you can prevent it from failing back? Because what we did is we did get a glitch. It's a glitch, but it was a service impacting glitch for a second. Can you tune it down so it doesn't as aggressively swap?
So even if it aggressively swaps, like I said a second ago, unplug, it's not going to affect anything. With the applications have no idea what's going on.
Well,
so,
it did. We went gray screen.
Little gray screen there, but most applications and environments don't know what's going on. But if you want to tune it itself, that's really just how you implement it. If you want to actually call it dampening, all right? So dampening is fully affected inside of ISI, so we can actually use dampening to do that.
So there is.
Yeah, absolutely. Everything you think about ISI is still there. All right, we've just augmented it and added more things to it. And actually, it was very little information we added to ISIS, by the way, to get all this.
I mean, not that the gray screen is a deal breaker for anybody who's seen this after the fact. It was minimal. It just,
Also, there's some active work going on with enhanced traffic.
Knowing this application, that's a win. I'm telling you right now, that's a win.